F with M1, the shoulder. However, because of the human anatomy, this distance more or less is a constant. We assume that it is a constant. So that is why we can describe this L1 in dependence on this angle alpha. Alpha, it is a constant, and independence on the angle beta, it's here. So this is the formula that describes L1. So now have a look. There is some deviation in between the horizontal line in the previous slide, in between this direction of M against the direction of the force F. So this is the small angle gamma. So this gamma definitely depends on beta. Because of walking, we're changing beta, and as a result, gamma is changed. So we can describe that M1 is equal to M, this one, as the constant, with a cosinus gamma. So this is the same gamma. This one, it is the same as here and as here. So that is why we see that gamma is a function of beta. So, and now we go to understand how gamma depends on beta following some movie. For instance, now we can calculate the force as a load with L cosinus M cosinus. Oh, so this is a mistake. This is gamma. Okay. So, and finally, we can calculate the ratio of F to P. So to compare how great is force F against P. So the typical dimensions of L and M are as follows: 250 and 300 millimeters, and alpha angle, this one, is around 10 degrees. And now have a look, really. So this angle and this angle are connected. And now let's go to have a look at the movie to try to understand what is the correlation between these two angles. Oh, sorry. Okay. You see this angle is changed? Now have a look. Yeah, and this angle also is changed. Again, have a look, it's tilted. And this tilt also is different. So now I'm extracting several pictures from this movie to identify the angles. For instance, from this one to this one, we have, this is a gamma angle approximately minus 45, and this is 60 beta. So this is a gamma in beta. For this one, we have 15, and here 15. And this is the opposite direction of gamma, so that is why 45 minus. And from this position, we have beta 0, gamma 0. So the deviation of the leg against the initial position is 0, and beta also is 0. So in this position, we have gamma around 0 and beta roughly 45. So, and this is the line, knowing the ratio between the gamma and beta angles, and this is the line that explains the ratio of in between F and P. So the highest low, and the highest force is at a very low angle just when we are starting to walk. Have a look. At this position, it is a higher force to the tendon. Now, falling down, and here we have the smallest one. So this is the reason that we can damage the tendon at the beginning of the step. At this position, because the force is very, very high. So the questions, please.
No.
Now we go to continue. Our previous liquid. So we have finished with the Newton and non-Newton liquids. Just to remind you that non-Newton liquids are characterized with a viscosity coefficient that depends on the velocity of the liquid. And this connects with the molecular structure. So now we have concluded that really it is a reason to measure the viscosity coefficient to identify molecular structure. Definitely, we can't say what is the design of the molecule, but we can say that molecular structure is changed or not. For instance, the viscosity coefficient becomes different because of some conditions, and this is the message to us that something was happened with the molecular structure of liquid. And now, how to measure this viscosity coefficient? One of the approaches was developed by physicist Stokes. And the idea was very simple. For instance, this is like the bolide, for instance, a metallic or some different material sphere that falls down. If it falls down with permanent velocity, or maybe just staying into the liquid, the forces that that work on this sphere are the following. Because of the motion, there is a friction force, the Newton friction force, Fb. So Stokes had calculated for the sphere case this friction force. It's equal to the radius of the sphere, velocity of the sphere falling down, and the viscosity coefficient. So next, there is an Archimedes force that trying to push up this sphere. The Archimedes force may be calculated if you know the density of the liquid. So that is why there is a weight, there is a friction force, and the Archimedes force. So the Archimedes force, the weight can be calculated if you know the radius, definitely we know, the density of this material, and g, this is a gravitation acceleration, or gravity acceleration. The Archimedes force is the same, but here we have the density of the liquid. Some questions here? Hello? Any questions?
No.
No.
So now let's collect all of the formulas together. And we have such a result, it's here below. So now we go to combine this result to get the viscosity coefficient. So this is the viscosity coefficient, and finally the result. So we have the radius, the gravity acceleration, the density of the sphere, of material of the sphere, and the density of liquid. So now, definitely there is a velocity. If you measure the velocity, and we know everything here, we can calculate the viscosity coefficient. Now again, if there is change of liquid, means something changed because of heating, because of the pathology, for instance, the velocity will become different and the viscosity coefficient differs too. So this is the index that some deviations of the molecular structure in liquid appear. So this technique we use, for instance, to identify properties of blood, urine. This is a typical laboratory measurement technique. Now we go to speak about the pressure within the flow. So here we need to mention the name Poisel from France. He had spent a lot of time to understand the connection in between pressure and velocity of the flow. For instance, this is a pipe, and this is a liquid that follows from left to right, for instance. Here, Poisel calculated the flow, Q. So for this, he used the radius of the pipe, and he selected some particle here at the distance r from the center of the pipe. So next, he said there is some ring, very, very small ring, that has a width dr, and the pressure works on this ring. If so, there is some flow dq that actually is localized within this ring. So the ring is moved, so means this flow also is going ahead. So now there is a v, the velocity of this ring movement. So following the definition, we can write that dq is equal to v, but v depends on r, definitely, and ds, the square of this ring, around the ring everywhere. So now, to calculate q, we need to integrate dq. So, if you go to integrate dq, we have vr, and ds we can describe as the radius r with 2 pi, the length of this ring, with its width dr. So 2 pi r dr, 2 pi are the constant. That is why I'm writing in the front, and we have the r dr. Is this clear? Lūdzu, jautājumu, ja nav skaidrs, lūdzu.
Bet tad, piemēram, šim mazajam rādījusam nav nozīmes tā garumam
Pagaidām
tikai...
mēs nezinām, jā, mēs tikai pieņemam, ka šīs gredzens ir ļoti šaurs, jā, un tāpēc mēs paņemam gredzena garumu, apļa garumu un pareizinājam, un sareizinājam ar gredzena, kā teikt, platumu, nu jā, platumu.
Jā, labi,
What is
paldies.
S?
Jā, lūdzu.
What is S again?
Yeah, please.
What is S again?
What?
S. What is S? The S.
S, ds. So this is the area of this ring. So this area.
Is it a square or is it a circle?
Square. This is square. Yeah.
Oh.
We are getting the length of the ring, 2 pi r, with the width of the ring. Is this clear?
Okay, so it's like taking a cylindrical pipe, but then taking a square
No,
section.
no. Just a second. Long straw again. So this is the ring. So, and this is a square. So that is why to calculate square S, I need to write, this is a radius, 2 pi r, the length of the entire ring, with this width, dr. Is this clear?
I still don't understand. What square, sir? What
So
square?
this one. So this one square.
You mean squared area, like the area?
Yeah. So if, for instance, I cut this ring and to extend it into the straight, like the straight line, you see, this is the ring extended. So this is equal to
Oh,
pi r, and this is dr.
okay. I think I get it again. Thank you.
Okay. Make sense?
Yes, it does. Thank you.
Okay.
Thank you.
So now we know everything except of this v, of the velocity. Let's calculate this one. Now we are getting the cylinder cutting off from the liquid, the cylinder, with the radius r. The entire cylinder has a movement with the velocity v because of the force that acts on this cylinder. And this is the friction force that works against the driving force F. The force F is definitely equal to the pressure difference P1 minus P2 with this square, PR square. This is the force, this one. The friction force, Fb, following the Newton formula, is equal to the viscosity coefficient, S dV dr, where S is this area, the side area of this surface. So around the cylinder. So that is why S is equal to 2 pi r, the length of this circle, with the length of the cylinder, L. Is this clear? flow.
Yeah.
So next, let's assume that this velocity is a constant and there is an equilibrium in between two forces. Means if the velocity is a constant following the second Newton law, the resultant force is equal to 0. This means that F is equal to FB. If so, we can write immediately that this one is equal to this one. And this is a formula that describes this equilibrium. From this formula, we can get dV. And this is for the case of the homogeneous motion with the motion when the velocity is a constant. But we have at least dV, that now we can use this dV for integration. So the integral of dV, so this means this is a constant. We have RdR from R to R. This is the radius of the pipe, and this is the radius of the cylinder. So if you finalize the integration, we have the formula for V. So actually, this is already the formula of V. So the formula of V, the integral of dV, is equal to the velocity at radius r here minus the velocity at the radius r. Now let us think, what is the velocity here? Following the Newton law, the velocity here is equal to, please open your conspect and have a look at the formula of friction, Newton experiment, the first one that we started to learn liquids.
0.
0, exactly. This experiment. So that is why you consider that V on R is definitely equal to 0. As a result, we have that this integral is equal to minus VR. And now we can write that this one is minus VR, and this minus VR must be equal to this one. And this is the final result. Any questions? You can ask me why I have changed the minus here but not here. Because this one with minus is the same as this one, so don't ask, okay. It's more simple to explain by this way. So I need to change minus here. Is this formula clear?
Yeah.
So to reiterate, sir, the R, the big R is the R of the entire
Of the pipe.
pipe, and then R, the small one is at a
The
specific
small one,
point
some
inside.
selected, yeah. We don't
Okay.
know where, but somewhere.
Okay, thank you very much.
So now we see that V depends on R, depends on the location within the flow. This is very important. And now we go to calculate the Q, the flow, because we know already VR. Now let's put this one to the integral and go for integration. And Q, we have to integrate from 0, means the center of the flow of the pipe, to the radius of the pipe. So if we go for integration, everything is a constant except of this one, because this is r squared. And now we need to integrate from 0 to r of this one. So this is a step of integration. We can separate the integral into two parts, integral of this one and integral of this one. This is r cubed. This is R square R. So step by step we are going. So I believe that you know that here we have to write R4 divided with 4 and to use the limits of integration from 0 to R. So finally we have this result that flow depends on the pressure difference. R means the radius of the pipe in the force power, divide with 8 viscosity coefficient and length of the pipe. Is this formula clear to you? Hello?
Yeah.
Okay. From this one, we have the formula for the pressure. Actually, this is the same formula as above, however, a little bit transformed to get pressure out. So now we have two formulas. One formula, the left one, is able to assist us to control flow, and this one assists us to control pressure. If you're speaking about the pipe, means the blood vessel, we can control here blood pressure, and here we can control the flow, blood flow. So we control the blood flow on the left, and here we can control blood pressure, means hypertonic treatment. From physics to treatment. And now let us go to consider what can be done to treat. What is the most important? That Q depends on R in the force power, means a little bit to change radius of the pipe, immediately the flow is changed. The same here, a little bit to change the radius of the pipe, means the blood vessel, and immediately the blood pressure is changed too. Now let us go for treatment. We're going now to treat our patient that has hypertony, means the increased blood pressure. What can be done following this formula? Please, your advices. Means we need to decrease pressure, means we need to decrease the difference in between P1 minus P2. What can be done to decrease blood pressure? Just follow the formula, please.
Samazināt viskozitāti.
To decrease viscosity, how?
Nu, padarīt asins vairāk šķidru, pievienot vairāk ūdeni.
Tas ir?
Nu, dzert vairāk ūdeni.
So drinking of water, yes. Second, if there is an acute situation of the patient, what can you do? To inject water.
Serum?
To inject water to decrease the viscosity coefficient. Is it clear? Hello.
Yeah.
So the next approach, what can be done? We have considered eta, and now let's go to consider the next one, L. What can be done with L to decrease pressure? Please.
Palielināt L vērtību.
L palielināt, ar to mēs samazināsim starpību.
Samazināt L vērtību, atvainojos.
Okay, to decrease L.
Yeah.
How? To decrease the length of blood vessels. How? Just one way, surgery. And we're doing this. The next one is Q. What can we do with Q to decrease the blood pressure here? What to do?
Samazināt.
How? To decrease Q, we need to do something. How? Q is provided because of, the flow is provided because of
Heart pumping.
To decrease Q, we need decrease what?
Sirdsdarbību.
Means
To decrease the radius?
yeah, we need to decrease the number of the beats by the heart. Means to decrease pulse. How? By some pharmacy, or to say to the patient, so please don't worry, be patient, and he will become patient. He will not be nervous. The heart pulse decreases, Q decreases too. Is this clear?
Yeah.
Yeah.
So the next one and the most powerful is R, because R is the force power. So to decrease pressure, we need to
Increase.
increase R, the radius of the blood vessels. How?
Temperatūra varbūt.
Nu, ja ir kādi aizkrustojumi, tad viņus vajadzētu tā kā atbrīvot.
Neesmu pārliecināts, tur jau ieslēdzas fizioloģija.
To eat less fats, perhaps?
No. We have the patient at the emergency situation. We need to do something.
Oh, vasodilators, the medicines that increase the radius.
What does it mean, this medicine? What does the medicine do?
It dilates the diameter of the blood vessels.
But how? What is the mechanism? So we need to increase.
It makes the wall thinner.
Pardon?
It makes the wall of the blood vessels thinner.
No, you'll kill your patient. Have a look. He has a high blood pressure, but we are gearing the medicine to decrease the wall of the pipe. The pipe is destroyed because of the high pressure. This is first. Second, to decrease the thickness of the wall, you need a long of time because the wall is designed of the cells. You need to have this time to reconstruct cell proliferation, etc. You see, so this is a long time. You don't have it. You need to operate very, very fast. 1 minute, 2 minutes, 10 minutes.
Varbūt kādus homeopātus vai nomierinošos līdzekļus dot, kas paliek. Bet nē.
Bet mēs runājam par radiusu, jā.
Jā.
Ar temperatūru to nevarētu ietekmēt?
Kā lūdzu?
Temperatūra nevar ietekmēt rādījus izmaiņu.
Mēs jau runājam, jā, par cik maino temperatūru, tur ieslēdzas visa organisma fizioloģija. Un kā tur būs, mēs nevaram sevišķi paredzēt. Okay, you are considering that pipe means the blood vessel is somewhere in the vacuum. But in reality, the blood vessel is surrounded by what? What is around the blood vessel?
Muscles.
Muscles, exactly. Exactly, muscles. That is why to extend the radius of the blood vessel, we need to
relax the muscles.
To relax the muscles, exactly. And there are two ways for this. First, to say to the patient again, be patient, relax, please. And the muscles are relaxed. Or the second one, to use a pharmacy that relaxes the muscles. Is this clear?
You mean anesthetics, basically?
Yes?
Anesthetics.
Let us go next. So we have considered everything. Now let's estimate what is the blood pressure decrease on 1 unit of the blood vessel length. So let's go to norm this blood pressure to the length. So we can calculate it if you know the viscosity of the blood, the velocity in different blood vessels, the S square, and the radius. So this is a table that demonstrates what is the diameter of the blood vessels, what are the velocities for aorta, arteries, veins, and capillaries. This is the viscosity coefficient for the blood. So this is in Pascal blood pressure, just to identify that 1 Pascal is 0.075 of mercury millimeter, because typically the medical doctors are measuring in mercury millimeter units. So, and this is a calculation. Have a look. This is a decrease per 1 meter, decrease of the pressure per 1 meter of the blood vessel length for hours, for arteries, and for veins. For arteries, rather large because they have a very high blood velocity, but nevertheless the order is the same. And now let's go to the capillaries. The capillaries are here. And now to compare the capillaries with the other blood vessels, I have got here the logarithm. Because the scale, have a look, 4 orders decreases the capillary blood pressure per 1 meter of length. And here, not so strong. I believe that this is the reason that the capillaries are short. They can't be long because the cells can't be delivered to the long capillary, to the long distance of the capillary, because blood pressure falls down for 4 orders per 1 meter. Here, the blood vessels doesn't fall down so much. That is why the cells, the products, for instance, in brackets, for blood vessel remodeling can be delivered. But here, the products to remodel the blood vessel of capillaries can't be delivered for long distances because the pressure is very, very small at the end. That is the reason that the capillaries are very short, somewhere here. Is this clear? Hello, the questions, please.
Viss skaidrs.
So next, Bernoulli law. So this is a very important law. It will come to see this law several times. He was born in Denmark, the current Denmark, but he had spent a lot of 7 years in St. Petersburg as a professor of mathematics, and he discovered this law when he was employed in St. Petersburg. This was the time of Peter the Great. He collected the strongest scientists from Europe to strengthen the economy of Russia. So Bernoulli idea was very simple. He actually employed the energy conservation law to the flow. The energy conservation law is on the screen, that the kinetic energy plus the potential energy is a constant. Means if the potential energy is changed, the kinetic energy must be changed too, and vice versa. We know this law. And he can employ this law to the flow. For instance, this is a flow. This is the pressure here. And pressure in the terms of the flow means the potential energy. Because of the pressure, the flow acquires the velocity. So the velocity means the kinetic energy of the flow. And so this is a formula by Bernoulli. He said, have a look, the potential energy means pressure, plus the kinetic energy of the flow, V squared to 2, and this is the density of this liquid. This must be the constant. Very simple formula. So again, P, pressure, rho, density, V, velocity. Now, let's come back to our blood vessel. We know that following the Bernoulli formula, if you increase velocity, the blood pressure must fall down. If this increased, this must fall down because of the constant here. So we know that the velocity here is equal to 0 because of the Newton experiment. It's equal to 0 here and equal to 0 here. Means the maximum velocity must be somewhere here. Is this clear? Oh.
Yeah.
Now let us predict the distribution of the pressure following the Bernoulli law. Where is the highest pressure and where is the lowest pressure? Please.
Tur, kur ātrums ir 0, tur spiediens būs maksimālais.
Okay, so if velocity is equal to 0, constant, the pressure must be the highest. Okay, this is the highest pressure area and this is the smallest pressure area. Vice versa against the velocity distribution. The question, please? No questions? Okay, now we have the break 5 minutes, and I remind you that today we have the test during 20 minutes. The test will be open 9:30 until 9:50. The test is devoted to mechanics. So now 5-minute breaks. So we're back. So now we need to consider that blood liquid has the particles and the cells. We can say particles. So if the particles are located here at the wall, they don't have movement, but they are pressed by the very high pressure here. Means the particles may be collected here without any movement. Do you hear me? Did them?
Yeah.
So, and this is rather danger because one layer is covered, the first layer of the particles is covered by the next one, and finally, the blood vessel cross section can become smaller. That is danger for the patient health. So at the center, we have a very fast movement of the particles. However, the particles here don't have movement and they are pressed to the walls. Not good. So some negative processes can be developed here. Non-proliferation of the cells, remodeling of the blood vessels, etc. So we need to get this particle from the wall to the center of the blood vessel and move from this place and move forward. What to do? To make motions of these blood vessels to mix everything that is inside. So this means sport. No other options. Just walking, exercising, do whatever you want, but do something with your blood vessels to prevent collection of the particles at the wall of the blood vessel. Is this clear for you?
Yeah.
So this is because of the Bernoulli law, Newton and Bernoulli. So next, during the systole, the blood flow goes ahead. However, we know that the blood vessel is surrounded by the muscles. When systole is over, don't have systole, the muscles are pressing on the blood vessel. So means no pressure inside of the blood vessel. However, there is a pressure from outside by the muscles. So the pressure here increases and blood is pressed out. Is this clear?
Yeah.
So because of the muscles, when systole is over as this diastole phase, disystole phase, the blood is pressed out. Also not so good. To prevent this, our blood vessels have the gates. This is a gate. Have a look. Blood vessel is going because of systole. The gate is open. The next is open. Now, the systole is over. No pressure, no flow. The gates are closed. And because of the muscle pressure, liquid can't come back, can't be returned because the gates are closed. Is the idea clear?
Yeah.
So these gates are named lamelles. So the next one, these are the cells, the particles at the walls. Systole, the particles can be pressed by the gate to the wall. Not so good. Next, when muscles are working, pressure increases because of the deformation of the blood vessel wall due to the muscles pressure. These cells are moved to the center, mix it, and are taken out. Have a look. We have spoken about the exercises. However, if the patient can't be moved, can't have a capacity to do movement, we need to do something with the muscles to stimulate the muscles to work, to press these particles out. So, by the message, by electrical stimulation, whatever, but we need to do this. And very important to keep the muscle of the human in so-called tonus. So now I'll show you the movie, short movie from the Russian TV translation. They had demonstrated these lamels like at the model. So this is a vein in the leg. This is the particles of the blood, and these are the lamels. So he's explaining that we need to move. So because of this, so the wave, the gate is open, and blood can be moved this direction. If the vein is extended, so the gate is open, and that is why the blood circulation is troubled. So he is speaking about the venous disease. Is it clear? Is it clear?
Yeah.
So this is the scheme of the blood vessel and the muscles. So when we have systole, you see everything is fine. Behind the systole, the vein, the blood vessel is pressed. And now a little bit Bernoulli law and the aircraft. So actually Bernoulli law explains how the aircraft is able to fly. So this is the wing of the aircraft. We provide the airflow by the engines, for instance, and have a look. Here, the airflow doesn't have any resistance, means the velocity of the airflow here is very high. However, here, the airflow has a resistance because of the wing. The velocity is lower. If the velocity is high, the pressure is lower. If the velocity is small, the pressure is high. So means velocity here is small, the pressure is high. The resulted pressure in this case is directed upstairs, means the wing is lifted and the aircraft may be elevated. Is this clear?
Sir,
Yeah.
I have a question regarding the blood flow of the blood flow in blood vessels.
Yes.
And say for example a blood vessel that has valves. So if you could go back, probably, I'm so sorry. Okay, so say for example, you see that where the valves attached to the blood is the point where the velocity is usually zero, due to the fact that it's the closest point to the walls of the well, the blood vessel. That is correct, right? The flow is zero.
Because the velocity here is zero, means blood pressure here is highest.
Okay, so does that in any technical way affect the blood flow in a good way? Because then no blood is going to be stuck within the blood vessel because it's all going to be pushed to the middle where the blood flow is not zero, or the valves themselves on their tips still make the blood flow zero, because technically that
No. They don't do the no. The valve, the gate, doesn't provide the flow. This is just the valve that prevents this liquid to come back.
So it doesn't affect the velocities you know, in
Minimal, like the hydraulic resistance.
okay. Thank you very much.
So we come back to this Bernoulli law to my mind next lecture, perhaps, when we speak about the speech apparatus of the human. Actually, we can speak because of this Bernoulli law. So, and I'll show you, we can say that we speak because of the aircraft capacity to fly, and aircraft flies because of our speaking, because the same law, the Bernoulli law, works for the speech, for voice generation. So the next point, hydraulic conductivity of the blood vessel system. So this is very approximately the circulation, the cycle of blood circulation of our body, of our organism. It's very developed, rather complicated. Different blood vessels are connected like the web. And so, but we're going to simplify to demonstrate what can be happen with the blood vessel system if, for instance, one large vessel is blocked. So this is a heart. This is a main artery that that blood flows through it. After that, there is a fork to some smaller blood vessels. They can be forked again, but we're going to consider very simple system. So each branch of this very simple system has a hydraulic resistance. So the hydraulic resistance of this one is R1, R2, R4, R5, and R3. So, and the flow is a constant starting from the heart and distributed over the entire organism. So the flow here is equal to the sum of the flows here. So following the flow formula, just to simplify it, we can say that this is a current. This is the difference of the potential, delta U. And 1 divided to R, this is the resistance. And actually, 1 divided to R, we can say that this is a conductivity, omega, and that is why the current is equal to the difference of the potential with omega. This is like from electricity. However, electricity had used this formula to describe the electrical current formula, because the physics of hydraulic processes became earlier than the physics of electricity. And so hydraulic processes became the analogs for electricity. Actually, this is the same formula following, the structure of the formulas are the same. And now our task is to identify this current, means the flow, independent on the conductivity. And conductivity we can calculate if you know the resistance. 1 to R, the resistance omega is equal to omega conductivity. So now have a look, the conductivity, this is the conductivity, depends on pi, so on the viscosity coefficient, length of the blood vessel, and again R in the force power. So just a little bit to change the radius of the blood vessel, tremendous changes come to the conductivity. So now let's go to calculate the conductivity of this branch, R1 and R3. The resistance we know, the summarized resistance is the sum of these two partial resistance, R2, R3. The conductivity we have to convert, 1 to 3 is equal to 1, R2 plus R3. So finally, we have 1 to omega 2 is R2, 1 to omega 3 is R3. Finally, we have the conductivity of this branch can be described by this way. Similar, we can describe this one. And the conductivities are summarized. The conductivity of these two branches, the summarized conductivity, is the sum of the conductivities. So means the conductivity of this one, 2, 3, 4, 5, is equal to the conductivity of this one plus the conductivity of this one. We know the conductivity of this one, it is here. And by the same way, we can write the conductivity of this one, it's here. So this is the conductivity of these two branches. And entire conductivity, very similar with the previous, is like this one, or the final formula for the summarized conductivity is here. Now, we see that the summarized conductivity depends on the conductivities by each blood vessel. If, for instance, some blood vessel is rather large and has rather high value of conductivity, I don't know, for instance, this one, and suddenly it is blocked because of some reason, definitely the summarized conductivity is changed. For instance, blocked because of spasm, for instance. Immediately it is changed too. In spite that this blood vessel is very, very far from the heart, but it has strong influence on the summarized conductivity because of the R in the fourth power. A little bit of spasm, a little bit muscles are pressed on the blood vessel, immediately the entire conductivity of the blood system is changed. What can be happen with the heart? If, for instance, somewhere is blood vessel blocked, the conductivity here falls down tremendously. The blood, the heart is getting hydraulic shock. This is like with the water pipe system. If suddenly in the city the pipe somewhere, large pipe is blocked suddenly, immediately the entire hydraulic water pipe system of the city may be damaged. The same we can meet with the heart, means the stroke. The questions, please. Please, the questions. Hello?
No.
Nav jautājumu.
No. So now, please go to Ortus. In 2 minutes, the test is open. Please pass the test. If you have some questions at the beginning, ask me. I'll stay somewhere 2-3 minutes. So good luck.